The Milky Way stretches across 100,000 light-years of space. And yet, if you could shrink it down to the size of a dinner plate, our entire solar system would be smaller than a single grain of sand, lost somewhere near the edge. That is the kind of vastness we are about to explore together. What lies within this enormous spiral of stars? And how does our tiny Earth fit into a galaxy so large that light itself takes thousands of centuries to cross it? If you find this journey through the cosmos as mind-bending as we do, please take a moment to hit the like button and subscribe to the channel. Your support helps us bring more incredible explorations of the universe to you. When we talk about distance in everyday life, we use measurements like feet, meters, or kilometers. You might say a store is 5 miles away, or a friend lives 20 kilometers down the road. These units work perfectly well for getting around on Earth. But the moment we leave our planet and start looking at the space between worlds, these familiar measurements become almost useless. Consider this simple example. The distance from your house to the grocery store might be 5 kilometers. You could walk it in an hour or drive it in a few minutes. That makes sense to your brain. You can picture it. You can feel what that distance means because you have experienced something like it before. Now think about the distance from Earth to the Moon. It is roughly 384,000 kilometers. That number is so much bigger than our trip to the grocery store that it starts to lose meaning. Sure, you can say the words, but can you really feel what almost 400,000 kilometers actually represents? Probably not. And that is just the Moon, our closest neighbor in space. The distance from Earth to the Sun is about 150 million kilometers. We have now jumped from hundreds of thousands to hundreds of millions. The numbers are getting so large that they stop feeling real. They become abstract symbols on a page, rather than actual distances you could ever hope to travel. This is exactly why scientists invented a new unit of measurement for distances within our solar system. They call it the Astronomical Unit, or AU for short. 1 AU is simply the average distance from Earth to the Sun. Instead of saying the Sun is about 150 million kilometers away, we can just say it is 1 AU away. This makes the math easier and helps us compare distances more clearly. Using this new unit, we can start to map out our cosmic neighborhood. Mercury, the closest planet to the Sun, orbits at about 0.4 AU. That means it is less than half the distance from the Sun that we are. Venus comes next at about 0.7 AU. Then comes Earth at 1 AU by definition. Mars sits at roughly 1.5 AU from the Sun. Already you can see how the AU system helps. Instead of juggling with millions and millions of kilometers, we have nice small numbers that show us the relative distances. Mercury is closer to the Sun than Earth. Mars is a bit farther out, simple and clean. But our solar system does not end with Mars. Beyond the red planet lies the asteroid belt, a region filled with rocky chunks of material that never quite came together to form a planet. The asteroid belt extends from about 2 to 4 AU from the Sun. After that come the giant planets, and this is where the distances really start to grow. Jupiter, the largest planet in our solar system, orbits at about 5.2 AU from the Sun. It is more than 5 times farther from the Sun than Earth is. Saturn, famous for its beautiful rings, sits at roughly 9.5 AU. Now we are almost 10 times the Earth-Sun distance away. Uranus orbits at about 19 AU, and Neptune, the last of the major planets, circles the Sun at approximately 30 AU. Think about that for a moment. Neptune is 30 times farther from the Sun than Earth is. If you could somehow drive a car from the Sun to Neptune at highway speeds, without stopping, it would take you over 5,000 years to make the trip. But Neptune is not the edge of our solar system, not even close. Beyond Neptune lies a vast region called the Kuiper Belt. This is a ring of icy bodies, frozen chunks of rock and ice that orbit the Sun at enormous distances. The Kuiper Belt extends from about 30 AU, where Neptune orbits, out to roughly 50 AU from the Sun. Pluto lives in the Kuiper Belt. Once considered our 9th planet, Pluto is now classified as a dwarf planet, one of many icy worlds in this distant region. Pluto's orbit is not a perfect circle like Earth's. It swings between about 29 AU and 49 AU from the Sun, sometimes coming closer to the Sun than Neptune, and sometimes traveling much farther away. The Kuiper Belt is home to thousands of known objects and likely millions more that we have not yet discovered. These frozen worlds are leftovers from the formation of our solar system, ancient relics that never got pulled into a planet. They drift silently through the darkness, so far from the Sun that our star appears as just a very bright star, rather than the blazing disk we see from Earth. If you were standing on Pluto, the Sun would look like a brilliant point of light in the sky. It would still be much brighter than any other star, but you would not feel its warmth. At that distance, the Sun's heat has spread out so much that Pluto's surface stays at temperatures cold enough to freeze nitrogen solid. Beyond the Kuiper Belt, the solar system continues to extend outward. Astronomers believe there is a region called the scattered disk, populated by icy objects that have been flung into highly elliptical orbits by gravitational encounters with Neptune. These scattered disk objects can travel hundreds of AU from the Sun before swinging back in closer. And then there is the Oort Cloud. This is the true edge of our Sun's gravitational influence, a spherical shell of icy bodies that surrounds our entire solar system. The Oort Cloud is so far away that it makes everything else we have discussed seem close by comparison. The inner edge of the Oort Cloud is thought to begin at around 2,000 AU from the Sun. That is 2,000 times the Earth-Sun distance. The outer edge may extend to 100,000 AU, or even further. To put this in perspective, the nearest star to our Sun, Proxima Centauri, is about 270,000 AU away. The Oort Cloud extends a significant fraction of the way to the next star. Objects in the Oort Cloud are so distant that they take millions of years to complete a single orbit around the Sun. They drift in the cold darkness, so far from our star that the Sun would appear as just another star among thousands, barely distinguishable from its neighbors. The Oort Cloud is believed to be the source of long-period comets, those visitors from the outer solar system that occasionally fall toward the Sun and develop spectacular tails as they warm up. When gravitational disturbances from passing stars or the galaxy itself nudge an Oort Cloud object, it can begin a long fall toward the inner solar system, eventually becoming visible to us as a comet. So our solar system is not just a collection of planets orbiting a star. It is an enormous structure that extends from the blazing surface of the Sun all the way out to the frozen darkness of the Oort Cloud, spanning potentially 100,000 AU or more. That is a distance so vast that light itself, traveling at the fastest speed possible in our universe, takes more than a year to cross from the Sun to the outer Oort Cloud. And yet, as enormous as our solar system is, it is just one tiny speck in the Milky Way galaxy. The galaxy contains hundreds of billions of stars, each potentially with its own system of planets and moons and asteroids and comets. Our solar system is like a single house in a city of hundreds of billions of houses, each separated by enormous distances. To travel between the stars, we need an even larger unit of measurement than the AU. This brings us to the light year. A light year is the distance that light travels in 1 year. Light moves at about 300,000 kilometers per second, so fast that it could circle Earth more than 7 times in a single second. Over the course of a year, light covers roughly 9.5 trillion kilometers. That number is so large it is meaningless to most human minds. 9.5 trillion kilometers. You cannot visualize that. You cannot feel it in your bones the way you can feel the distance to the grocery store. But what you can understand is the concept of light travel time. When you look up at the night sky and see a star, the light entering your eyes left that star years, decades, centuries, or even millennia ago. You are not seeing the star as it is right now. You are seeing it as it was when that light began its journey. Looking out into space is literally looking back in time. The closest star to our Sun is Proxima Centauri, part of the Alpha Centauri system. It is about 4.2 light years away. That means the light you see from Proxima Centauri tonight left that star more than 4 years ago. If something dramatic happened to Proxima Centauri right now, we would not know about it for over 4 years. 4 light years might not sound like much compared to the size of our solar system's Oort Cloud, but remember that a light year is an enormous distance. 4 light years equals roughly 37 trillion kilometers. If you could travel at the speed of our fastest spacecraft, it would take you tens of thousands of years to reach Proxima Centauri. The Milky Way galaxy spans about 100,000 light years from edge to edge. That means light takes 100,000 years to cross our galaxy. When you see light from stars on the far side of the Milky Way, you are seeing light that left those stars when woolly mammoths and saber-toothed cats still roamed Earth. The universe operates on timescales that make human history seem like the blink of an eye. Our Sun is not sitting still in the galaxy. It is moving, orbiting the center of the Milky Way, just like Earth orbits the Sun. But while Earth takes 1 year to complete an orbit around the Sun takes about 230 million years to complete one orbit around the galactic center. Think about what that means. The last time our solar system was in this part of its orbit around the galaxy, dinosaurs had not yet appeared on Earth. The next time we return to this position, humans will likely be long gone, either extinct or evolved into something unrecognizable. Our Sun has completed only about 20 orbits around the galaxy since it formed 4.5 billion years ago. The Sun moves through the galaxy at roughly 220 kilometers per second. That sounds incredibly fast, and it is. But the galaxy is so enormous that even at this tremendous speed, it still takes hundreds of millions of years to complete a single lap. As the Sun orbits the galactic center, it also bobs up and down through the galactic disk, like a horse on a carousel. It takes about 64 million years to complete one vertical oscillation. Some scientists have wondered if this bobbing motion might correlate with mass extinction events on Earth, as the solar system passes through regions of the galaxy with different densities of cosmic dust and debris. Our Sun sits in one of the spiral arms of the Milky Way, specifically in a region called the Orion Arm, or sometimes the Orion Spur. We are about 27,000 light years from the galactic center, roughly halfway between the center and the outer edge of the galaxy's disk. From our position, we can see the band of the Milky Way stretching across the night sky. That milky glow is actually the combined light of billions of stars, so distant that they blend together into a continuous ribbon of light. When you look at the Milky Way on a dark night, you are looking into the disk of our galaxy, seeing the accumulated glow of countless suns. The Milky Way is a barred spiral galaxy, one of the most common types of galaxies in the universe. It has a central bulge, a flat disk with spiral arms, and a surrounding halo of older stars and mysterious dark matter. Each of these components tells us something different about how our galaxy formed and evolved over billions of years. The central bulge is the densest part of the galaxy, a roughly spherical concentration of stars near the galactic center. This bulge is about 10,000 light-years across and contains some of the oldest stars in the Milky Way. Many of these ancient stars formed within the first billion years after our galaxy came into existence. The stars in the bulge tend to be older and redder than stars in the disk. They follow more random orbits, moving in all directions rather than the orderly circular paths of disk stars. The bulge is a crowded place, with stars packed much more closely together than in our neighborhood of the galaxy. At the very center of the bulge lies something extraordinary. Hidden behind clouds of dust and gas sits a supermassive black hole. And yet, object so massive that nothing, not even light, can escape its gravitational pull once something gets too close. This black hole is called Sagittarius, a star, often written as Escrow star. The name comes from its location in the constellation Sagittarius as seen from Earth. For decades, astronomers suspected something massive lurked at the center of our galaxy, but direct evidence proved difficult to obtain. The breakthrough came from patient observation. Scientists tracked the motions of stars near the galactic center for years and years. They watched these stars zip around at tremendous speeds, following tight orbits around something invisible. By studying these orbits, astronomers could calculate the mass of whatever was pulling on these stars. The results were stunning. The invisible object at the galactic center contains about 4 million times the mass of our Sun, all packed into a region smaller than our solar system. The only thing that could be that massive and that compact is a black hole. One star in particular, called S2, has provided incredible data about Sagittarius A star. S2 orbits the black hole with a period of about 16 years. At its closest approach, it passes within just 17 light hours of the black hole, moving at nearly 3% the speed of light. Watching S2 and other nearby stars has allowed astronomers to test Einstein's theory of general relativity under extreme conditions. In 2022, astronomers released the first actual image of Sagittarius A star, captured by the Event Horizon Telescope. This network of radio telescopes around the world worked together to create an Earth-sized virtual telescope capable of resolving the shadow of the black hole. The image shows a ring of glowing gas surrounding a dark central region, direct visual evidence of the monster at the heart of our galaxy. Despite its enormous mass, Sagittarius A star is currently quiet compared to black holes in other galaxies. It is not actively consuming large amounts of material. The gas and dust near it form a relatively calm accretion disk rather than the blazing fury seen in more active galactic centers. Our galaxy's central black hole seems to be in a period of relative dormancy. But it was not always this way. Evidence suggests that Sagittarius A star was much more active in the past. Astronomers have detected what appear to be bubbles of hot gas extending above and below the galactic plane, structures that may have been created by past outbursts from the central black hole. These Fermi bubbles extend 25,000 light-years in each direction, testament to the enormous energy the black hole once released. Surrounding the central bulge is the galactic disk, the flattened pancake-shaped structure that contains most of the Milky Way's visible matter. The disk is where you find the spiral arms, the regions of active star formation, and our own solar system. The disk is about 100,000 light-years across, but only about 1,000 light-years thick at our location. Toward the center, the disk thickens somewhat, but it remains relatively thin compared to its width. If you could see the Milky Way from the side, it would look like a dinner plate with a bulge in the middle, or perhaps a fried egg with the yolk representing the central bulge. The spiral arms are not solid structures, but rather density waves, patterns of compression that move through the disk like ripples on a pond. As gas and dust pass through these denser regions, they get squeezed together, triggering the birth of new stars. The bright young stars and glowing gas clouds light up the spiral arms, making them visible against the darker background of older stars. Our Milky Way has 4 major spiral arms, plus several smaller arm segments. The major arms are named after the constellations where we see them from Earth. The Perseus arm and the Sagittarius arm are 2 of the most prominent. Our Sun sits in the Orion arm, a smaller arm segment located between Perseus and Sagittarius. The spiral pattern rotates around the galaxy, but at a different speed than the stars themselves. Stars move in and out of spiral arms over time. Our Sun has passed through multiple spiral arms during its history, and it will continue to drift from arm to arm as it orbits the galactic center. Star formation in the Milky Way happens primarily in the spiral arms and in the central regions near the galactic bar. The bar is a structure of stars that extends across the center of the galaxy, a common feature in spiral galaxies. Our galaxy's bar is estimated to be about 27,000 light-years long, oriented at an angle to our line of sight from Earth. The bar influences the orbits of stars throughout the central region of the galaxy. It channels gas toward the galactic center and affects the shape of the inner spiral arms. Understanding the bar is crucial for understanding the dynamics of our galaxy as a whole. Beyond the disk lies the galactic halo, a roughly spherical region that extends far above and below the plane of the disk. The halo contains old stars, globular clusters, and enormous amounts of dark matter. It represents some of the earliest structures in our galaxy, the remnants of the Milky Way's formation billions of years ago. The stellar halo is populated by ancient stars, some of the oldest in the entire galaxy. These stars formed when the universe was young, before the disk had fully assembled. They follow random orbits that take them high above and below the galactic plane, passing through the disk periodically, but never settling into the orderly circular paths of disk stars. Globular clusters are among the most striking objects in the halo. These are dense, spherical collections of stars, each containing hundreds of thousands to millions of stars packed into a relatively small volume. About 150 globular clusters orbit the Milky Way, distributed throughout the halo. The stars in globular clusters form together from the same cloud of gas and dust, so they have similar ages and compositions. Most globular cluster stars are extremely old, typically between 10 and 13 billion years old. They are among the oldest objects we can study in detail, providing windows into the early universe. Globular clusters follow elliptical orbits around the galactic center, plunging through the disk and swinging far out into the halo before falling back again. Some clusters have orbits that take millions of years to complete. They are cosmic nomads, wandering through the galaxy on paths established when the Milky Way was first forming. Above the halo, some astronomers have detected evidence of an even more extended structure called the galactic corona. This is a vast region of extremely hot gas that surrounds the entire galaxy, extending perhaps 200,000 or 300,000 light-years from the galactic center. The corona is so hot that it glows in X-rays, a faint halo of radiation surrounding our stellar city. The corona may contain a significant fraction of the Milky Way's normal matter. Gas in this region is extremely thin, much less dense than the best laboratory vacuum on Earth. But because the corona covers such an enormous volume, the total mass adds up to something substantial. Understanding the corona is an active area of research as scientists try to account for all the matter in and around our galaxy. Now we come to one of the greatest mysteries in modern astronomy. The visible matter in the Milky Way, the stars and gas and dust and everything else we can see, is only a small fraction of the galaxy's total mass. Most of our galaxy's mass consists of something invisible, something that does not emit or absorb light, something we call dark matter. The evidence for dark matter comes from studying how the galaxy rotates. Stars orbit the galactic center at different speeds depending on their distance from the center. Near the center, where gravity is strongest, stars move faster. Farther out, where gravity is weaker, stars should move slower. This is exactly what we see in our solar system, where Mercury zips around the Sun much faster than distant Neptune. But when astronomers measured the rotation speeds of stars throughout the Milky Way, they found something strange. Stars in the outer parts of the galaxy were moving too fast. Based on the visible mass of stars and gas, those outer stars should be moving much slower than they actually are. Something invisible must be providing extra gravitational pull to keep those stars moving so quickly. The solution to this puzzle is dark matter. If the Milky Way is surrounded by a vast halo of invisible matter, that matter would add extra gravity throughout the galaxy. Stars in the outer regions would feel this extra pull and would orbit faster than they would based on visible matter alone. The rotation speed of stars stays roughly constant even at large distances from the center, a phenomenon called a flat rotation curve. Nobody knows what dark matter actually is. It does not emit light, it does not absorb light, it does not interact with normal matter except through gravity. We cannot see it, touch it, or detect it with any instrument designed to find normal particles. We only know it exists because of its gravitational effects on the matter we can see. Scientists have proposed many possibilities for what dark matter might be. Some think it could be a new type of elementary particle that we have not yet discovered. Others suggest it might be related to modifications of our understanding of gravity. Experiments around the world are trying to detect dark matter particles directly, but so far, no one has succeeded. What we do know is that dark matter makes up roughly 85% of the Milky Way's mass. The stars and gas and dust that we can see, everything that glows in the night sky, represents only about 15% of our galaxy's total material. We live in a galaxy dominated by invisible matter, surrounded by darkness that shapes our cosmic home. The dark matter halo extends far beyond the visible boundaries of the Milky Way, reaching perhaps 600,000 light-years from the galactic center. This means the dark matter halo is several times larger than the disk of visible stars. We exist in a small, bright island surrounded by an ocean of mysterious darkness. Dark matter played a crucial role in the formation of galaxies. In the early universe, dark matter began clumping together under its own gravity before normal matter could do the same. These dark matter clumps provided gravitational wells that attracted normal matter, allowing gas to collect and eventually form the first stars and galaxies. Without dark matter, the universe might look very different today. Let us now put together everything we have learned about the structure of our galaxy. The Milky Way spans about 100,000 to 200,000 light-years across its disk. Recent measurements suggest the disk might extend even farther than we once thought, with faint outer regions reaching far beyond the bright spiral arms. The disk is roughly 1,000 light-years thick at our location, thickening toward the center. It contains most of the galaxy's gas and dust, the raw materials for making new stars. Young hot stars populate the spiral arms, while older cooler stars spread throughout the disk. The central bulge extends about 10,000 light-years across, containing older stars and the supermassive black hole Sagittarius A star at its heart. A bar of stars stretches across the center, influencing the structure of the inner galaxy. The halo surrounds the disk, extending far above and below the plane. It contains old stars, globular clusters, and the vast dark matter component that dominates the galaxy's mass. The corona adds even more hot gas far from the disk. Our Sun sits in the Orion Arm, about 27,000 light-years from the galactic center. We are roughly 2/3 of the way from the center to the edge of the disk. From our position, we see the Milky Way stretching across the sky, a band of light marking the plane of our galaxy. If you could travel outside the Milky Way and look back at our galaxy from above, you would see a beautiful spiral structure. Bright arms would wind outward from the central regions, traced by hot young stars and glowing gas clouds. Dark lanes of dust would follow the inner edges of the arms, the raw material waiting to become the next generation of stars. From the side, the galaxy would look thin and flat, a disk of light with a bright bulge in the middle. The halo would be harder to see, populated by individual stars too spread out to form a continuous glow. But the dark matter halo would be there, invisible but present, its gravity shaping everything you could see. Our galaxy is not alone in the universe. It is part of a collection of galaxies called the Local Group, a gathering of more than 80 galaxies bound together by gravity. The Local Group spans about 10 million light-years across, a neighborhood of galaxies centered on two dominant members. The Milky Way is one of those dominant members. The other is Andromeda, also known as M31. Andromeda is the largest galaxy in the Local Group and the nearest large spiral galaxy to our own. It lies about 2.5 million light-years away, close enough that you can see it with the naked eye on a dark night. When you look at Andromeda, you are seeing light that left that galaxy 2.5 million years ago, when early human ancestors were just beginning to walk upright on the African savanna. The photons entering your eyes tonight have been traveling through space since before modern humans existed. Andromeda is larger than the Milky Way, containing perhaps 1 trillion stars compared to our galaxy's 2 to 400 billion. It spans about 220,000 light-years across, making it roughly twice the diameter of our galaxy. Its halo extends even farther, perhaps blending with the outer reaches of our own galaxy's halo. For many years, scientists debated which galaxy was more massive, the Milky Way or Andromeda. Recent measurements suggest the Milky Way might actually be more massive despite having fewer stars, thanks to our galaxy's more extensive dark matter halo. The verdict is not yet final, as measurements continue to improve. The Milky Way and Andromeda are approaching each other. Despite the overall expansion of the universe pushing galaxies apart, our two galaxies are close enough that their mutual gravitational attraction overcomes this expansion. They are falling toward each other at about 110 kilometers per second. In about 4 to 5 billion years, the Milky Way and Andromeda will collide. But do not imagine this as a violent crash. Galaxies are mostly empty space. The distances between stars are so vast that when galaxies merge, individual stars almost never actually collide. Instead, the galaxies will pass through each other, their shapes distorted by gravitational interactions. The collision will trigger tremendous bursts of star formation as gas clouds compress and collapse. Tidal forces will fling stars into new orbits, creating long streams of material stretching between the galaxies. Over hundreds of millions of years, the two galaxies will fall together again and again, eventually merging into a single larger galaxy. Astronomers have nicknamed this future combined galaxy Milkomeda, or sometimes Milkdromeda. It will likely be an elliptical galaxy, a smooth, featureless blob of stars rather than the beautiful spirals we see today. The spiral structure will be destroyed in the merger, leaving behind something very different from either parent galaxy. Our solar system will probably survive this galactic collision. The Sun will be near the end of its life by then, swollen into a red giant star that has already consumed Earth. But whatever remains of our solar system will likely continue orbiting within the merged galaxy, perhaps flung into a new orbit far from where we started. Besides Andromeda, the local group contains another significant spiral galaxy called the Triangulum Galaxy, or M33. Triangulum is smaller than both the Milky Way and Andromeda, spanning about 60,000 light-years across. It lies about 3 million light-years from Earth. Beyond Andromeda, in the same general direction, Triangulum is gravitationally bound to Andromeda and may eventually fall into the larger galaxy even before the Milky Way does. Some simulations suggest Triangulum will join the Milky Way-Andromeda collision, creating a three-way merger. The ultimate fate of the Triangulum galaxy depends on its exact orbit, which remains somewhat uncertain. The local group also contains many smaller galaxies, the dwarf galaxies that orbit around the larger spirals like moons around planets. The Milky Way has numerous dwarf galaxy companions, including the Large Magellanic Cloud and the Small Magellanic Cloud, visible from the southern hemisphere as fuzzy patches of light separate from the main band of the Milky Way. The Large Magellanic Cloud is about 14,000 light-years across and contains several billion stars. It lies about 160,000 light-years from the Milky Way, close enough that it is being gradually pulled apart by our galaxy's gravity. The Small Magellanic Cloud is even smaller, about 7,000 light-years across, and sits about 200,000 light-years away. Both Magellanic Clouds are irregular galaxies, lacking the neat spiral structure of the Milky Way. They are probably dwarf spiral or barred galaxies that have been distorted by gravitational interactions with our galaxy. Streamers of gas connect the Magellanic Clouds to each other and to the Milky Way, evidence of the gravitational dance they are performing. The Magellanic Clouds are being consumed by the Milky Way. Over billions of years, they will spiral closer and closer, eventually merging with our galaxy completely. This is a common fate for dwarf galaxies that get too close to larger neighbors. The Milky Way has absorbed many dwarf galaxies over its history, and it will absorb many more in the future. Evidence for these past mergers shows up in the halo of the Milky Way. When a dwarf galaxy gets ripped apart, its stars spread out into long streams that orbit the galaxy for billions of years before fully mixing in. Astronomers have identified several of these stellar streams, ghostly remnants of galaxies that no longer exist as independent structures. The Sagittarius Dwarf Elliptical Galaxy is currently being torn apart by the Milky Way. It is a small galaxy, about 10,000 light-years across, that is passing through the disk of our galaxy. Tidal forces are stripping stars away from it, creating streams of stars that wrap around the Milky Way. In another 100 million years or so, the Sagittarius dwarf will cease to exist as a separate galaxy. This process of smaller galaxies being absorbed by larger ones is how galaxies grow over cosmic time. The Milky Way was not always as large as it is today. It has grown by accumulating dwarf galaxies, adding their stars and gas to its own. The merger with Andromeda will be the largest such event in our galaxy's history, but the basic process is the same. The local group itself is not the largest structure in our cosmic neighborhood. It is part of a larger collection of galaxy groups and clusters called the Virgo supercluster. Superclusters are enormous structures containing thousands of galaxies spread across hundreds of millions of light years. The Virgo supercluster is named after the Virgo cluster, a dense concentration of galaxies at its center. The Virgo cluster contains over 1,000 galaxies packed into a region about 15 million light-years across. It lies roughly 50 million light-years from the Milky Way and exerts a gravitational pull on everything in the supercluster. The local group sits near the outer edge of the Virgo supercluster, relatively far from the dense center. We are being pulled toward the Virgo cluster, though the pull is not strong enough to overcome the overall expansion of the universe. The galaxies in our supercluster are slowly spreading apart, though not as fast as more distant galaxies. But even the Virgo supercluster is not the largest structure we belong to. In 2014, astronomers announced the discovery of an even larger structure called the Laniakea supercluster. Laniakea means immeasurable heaven in Hawaiian, an appropriate name for a structure of such staggering size. Laniakea contains over 100,000 galaxies spread across 500 million light-years. It includes the Virgo supercluster, along with several other superclusters that were previously thought to be separate structures. All of these galaxies are flowing together toward a common gravitational center. That common gravitational center is known as the Great Attractor, one of the most mysterious regions in our cosmic neighborhood. The Great Attractor is a concentration of mass about 250 million light-years away, in the direction of the constellations Centaurus and Hydra. Everything in Laniakea, including our Milky Way, is being pulled toward this region. We cannot directly see the Great Attractor because it lies behind the plane of our galaxy. The disk of the Milky Way blocks our view in that direction, filled with dust and stars that obscure whatever lies beyond. This region of sky is sometimes called the zone of avoidance because so few distant galaxies can be observed there. Despite the difficulty in seeing it directly, astronomers have studied the Great Attractor through radio waves and infrared light, which can penetrate the dust of our galaxy. They have found a massive concentration of galaxies in that region, including several large galaxy clusters that together create an enormous gravitational well. The Norma cluster is one of the major galaxy clusters near the Great Attractor. It contains thousands of galaxies packed into a relatively small volume. Other clusters in the region add to the gravitational pull, creating a kind of cosmic drain that everything in Laniakea is slowly circling toward. But the Great Attractor is not the final destination. Astronomers have discovered that the Great Attractor itself is being pulled toward an even larger structure called the Shapley supercluster, located about 650 million light-years away. The Shapley supercluster is one of the most massive structures in the observable universe, and its gravity influences everything for hundreds of millions of light-years around. Understanding these enormous structures helps us see the universe at its largest scales. Galaxies are not randomly scattered through space. They cluster together into groups, Groups cluster into clusters, clusters join into superclusters, and superclusters connect along vast filaments of matter that stretch across billions of light years. This arrangement of matter is called the cosmic web. If you could zoom out far enough to see the universe at its largest scales, you would see galaxies arranged along threads and sheets surrounding enormous empty voids. The web-like pattern formed in the early universe as gravity amplified tiny fluctuations in the distribution of matter, pulling matter together into filaments while emptying out the spaces between. The voids between filaments are not completely empty, but they contain far fewer galaxies than the filaments and clusters. Some voids span hundreds of millions of light years across, truly empty spaces where few galaxies exist. Our local group sits within a relatively average region of the cosmic web, not in the densest structures, but not in the emptiest voids either. Now we need to confront an important question. How large is the universe? Is there an edge to space, a boundary beyond which nothing exists? These questions have fascinated humans for thousands of years, and modern astronomy has provided some surprising answers. The universe began about 13.8 billion years ago in an event we call the Big Bang. At that moment, all the matter and energy in the universe was compressed into an incredibly hot, dense state. Space itself began to expand, carrying matter with it and cooling as it grew. Light from the earliest moments of the universe has been traveling toward us ever since. The oldest light we can see comes from a time about 380,000 years after the Big Bang, when the universe cooled enough for light to travel freely through space. Before that time, the universe was so hot and dense that light could not travel far without being scattered. This oldest light is called the cosmic microwave background, or CMB for short. It fills the entire universe, coming at us from every direction. Originally, this light was extremely hot, glowing bright orange like a furnace, but the expansion of space has stretched it out, shifting it to much longer wavelengths in the microwave part of the spectrum. When scientists first detected the CMB in 1964, they confirmed one of the most important predictions of the Big Bang theory. The CMB is like a baby picture of the universe, showing us what the cosmos looked like when it was less than 400,000 years old. Its existence proves that the universe was once much hotter and denser than it is today. The CMB is not perfectly uniform. There are tiny variations in its temperature from place to place, differences of only 1 part in 100,000. These tiny fluctuations represent the seeds of all the structure we see in the universe today. Regions that were slightly denser in the early universe grew into the galaxies and clusters we observe today. Regions that were slightly less dense became the voids between structures. The CMB acts as a kind of wall marking the edge of what we can observe. We cannot see anything older than the CMB because the universe was opaque before that time. It is like trying to look through a thick fog that clears suddenly. We can see everything after the fog cleared, but nothing from before. This brings us to an important concept called the observable universe. The observable universe is not the entire universe. It is the region of space from which light has had time to reach us since the Big Bang. Beyond this region, light simply has not had enough time to make the journey, no matter how long it has been traveling. The observable universe forms a sphere centered on Earth. But this is not because we are at any special location. Every observer anywhere in the universe would see their own observable universe centered on themselves. It is like standing in the middle of a flat plane. You can see a certain distance in every direction before the horizon cuts off your view. Every person standing on the plane would see their own horizons centered on themselves. The radius of the observable universe is not simply 13.8 billion light-years, which is what you might expect from the age of the universe. It is actually much larger, about 46 billion light-years. This is because space itself has been expanding while the light was traveling. An object that emitted light toward us 13.8 billion years ago has since moved much farther away due to the expansion of space. The full diameter of the observable universe is about 93 billion light-years. This is the total size of the sphere from which we could theoretically receive light. Everything within this sphere is part of our observable universe. Everything beyond this sphere is forever invisible to us. The observable universe contains roughly 2 trillion galaxies. That is 2,000 billion galaxies, each containing anywhere from millions to trillions of stars. The total number of stars in the observable universe is something like 1 followed by 24 zeros, a number so large that it has no everyday meaning. But here is the most mind-bending part. The observable universe is almost certainly not the entire universe. Space likely extends far beyond the limits of what we can see. Most cosmological theories suggest that the universe is vastly larger than the observable portion, perhaps infinitely larger. If the universe is infinite, then there is no edge, no boundary, no place where space ends. Space just goes on forever in every direction, filled with more galaxies and more stars without end. We would be living in a universe of truly infinite extent, where our observable universe is just a tiny bubble in an endless sea. Even if the universe is finite, it might have no edge. Imagine the surface of Earth. You can travel around it in any direction without ever reaching an edge, because it curves back on itself. The universe might be similar, curved in a higher dimension that we cannot directly perceive. You could travel in a straight line forever and eventually return to where you started, having circumnavigated the cosmos. Current measurements suggest the universe is very close to flat, meaning it does not curve back on itself in any obvious way. If there is any curvature, it is so slight that the universe would need to be at least 400 times larger than the observable portion for us to detect it. The universe might be infinite, or it might be finite but unimaginably vast. Adding to this picture is the discovery that the universe is not just expanding, but accelerating in its expansion. In 1998, astronomers studying distant supernovae made a shocking discovery. The expansion of the universe is not slowing down as gravity pulls matter together. Instead, it is speeding up, driven by something we call dark energy. Dark energy is a property of space itself, a kind of negative pressure that pushes space apart. We do not know what dark energy actually is, any more than we know what dark matter is. We only know it exists because of its effects on the expansion of the universe. Dark energy makes up about 68% of the total energy content of the universe. Dark matter makes up another 27%. Normal matter, the stuff we can see and touch and study, makes up only about 5%. We live in a universe dominated by mysterious dark components that we barely understand. The accelerating expansion has profound implications for the future of the cosmos. As space expands faster and faster, distant galaxies will recede from us at ever greater speeds. Eventually, they will recede so fast that light from them will never reach us. They will cross our cosmic horizon and disappear from our observable universe forever. In the very distant future, trillions of years from now, the observable universe will be much emptier than it is today. Distant galaxies will have faded from view, leaving only our local group of galaxies visible. The cosmic microwave background will have stretched to wavelengths so long that it becomes undetectable. Future astronomers, if any exist, might look out at the sky and see only their own galaxy, with no evidence that the vast cosmos we observe today ever existed. This is the universe we inhabit, an expanding space filled with hundreds of billions of galaxies, each containing hundreds of billions of stars. A cosmos that began in fire and will end in cold darkness. A universe where our Milky Way is one unremarkable galaxy among 2 trillion, floating in a sea of dark matter and dark energy. But what lies beyond the observable universe? What exists in the regions of space from which light has not yet reached us? Some theories suggest that the answer is simply more of the same. More galaxies, more stars, more planets, extending perhaps forever in every direction. The universe beyond our horizon might look much like the universe we can see, governed by the same physical laws and containing similar structures. Other theories are far more exotic. The concept of the multiverse suggests that our universe might be just one of many universes, each with its own properties and perhaps its own physical laws. These other universes might be completely separate from ours, forever beyond our ability to observe or interact with them. The simplest version of the multiverse comes from the idea that the universe is infinite. If space goes on forever, and matter is distributed throughout all of it, then every possible arrangement of matter must occur somewhere. There would be regions of space identical to our observable universe, containing copies of you and me and everything we know. There would be regions slightly different and regions completely different, all coexisting in an infinite cosmos. A more complex version of the multiverse comes from inflationary cosmology. Inflation is a theory that describes a period of extremely rapid expansion in the very early universe, a fraction of a second after the Big Bang. According to some versions of inflation, this process might happen repeatedly, spawning new bubble universes that separate from each other forever. In this picture, our universe is one bubble in an endless foam of universes. Each bubble might have different physical constants, different laws of physics, different histories. Some bubbles might be completely inhospitable to life, while others might contain civilizations far beyond our own. We would never be able to communicate with these other bubbles or prove their existence definitively. An even stranger possibility comes from string theory, a framework for physics that attempts to unify quantum mechanics and gravity. String theory suggests there might be an enormous number of different ways to configure the fundamental parameters of physics, perhaps 10 to the 500th power different possibilities. Each of these configurations might represent a different universe with different physical laws. These ideas are speculative, far beyond what we can currently test or prove, but they show how far our understanding of the cosmos has come. We have gone from thinking Earth was the center of everything to realizing we are one planet orbiting one star in one galaxy among trillions in an observable universe that might itself be a tiny fraction of all that exists. Through all of this, the Milky Way remains our home. This vast spiral of stars, spanning 100,000 light years across, containing hundreds of billions of stars and countless planets, is where humanity arose and where we live today. We have never traveled beyond our own solar system, and we may never journey to other galaxies, but we have learned to see the cosmos as it truly is. The atoms in your body were forged in the hearts of stars that lived and died long before our sun was born. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of it was created through nuclear fusion in stellar cores or in the violent explosions of dying stars. You are literally made of stardust, a piece of the universe that has become aware of itself. Every element heavier than hydrogen and helium was created inside a star. The first generation of stars, born from the primordial gas of the early universe, contained only those two lightest elements. They burned through their fuel and exploded, scattering heavier elements into space. The next generation of stars formed from this enriched material, building even heavier elements and scattering them in turn. This cycle has repeated countless times over the history of the universe. Each generation of stars has added more heavy elements to the cosmic mix. Our solar system formed from a cloud of gas that had been enriched by multiple generations of stellar deaths. The planets, the oceans, and all living things on Earth are made from this recycled stardust. When you look up at the Milky Way stretching across the sky, you are looking at your cosmic ancestry. Those distant stars are your relatives, siblings born from the same stellar nurseries, forged from the same raw materials. The galaxy is not just our address in the cosmos, it is our family history written in light. Let us return now to the question of scale, because it is worth exploring just how incomprehensibly vast these distances really are. We have talked about light years and megaparsecs, about millions and billions, but numbers like these slip through the mind without leaving much of an impression. We need to find better ways to feel the size of the cosmos. Imagine you could shrink the entire Milky Way galaxy down until it was the size of a frisbee, about 25 centimeters across. At this scale, our sun would be smaller than an atom. You could not see it with any microscope because it would be far too small. The distance between our sun and the nearest star would be about the thickness of a human hair. All those vast interstellar distances that we cannot cross in 1,000 lifetimes would become the width of a single hair on your head. Now imagine trying to find our solar system on this frisbee-sized galaxy. You would need to look about 2/3 of the way from the center to the edge, in one of the spiral arms. Even if you knew exactly where to look, you would see nothing. The sun and all its planets, everything that makes up our entire solar system, would be invisible at this scale. We would be lost in the immensity of the galaxy, impossible to find. Here is another way to think about scale. Suppose you wanted to build a scale model of our galaxy in your backyard. You decide to make each star the size of a grain of sand. The Milky Way contains roughly 200 billion stars, so you would need about 200 billion grains of sand. That is a lot of sand, but perhaps not impossible to imagine. But here is the problem. At this scale, with stars represented by grains of sand, the model galaxy would need to be about 5 million kilometers across. That is more than 12 times the distance from Earth to the Moon. Your backyard model would extend far beyond the Moon and most of the way to Mars. Even shrinking stars to grains of sand does not make the galaxy small enough to comprehend. The distances between stars are so enormous that space is almost entirely empty. If you picked a random point in interstellar space, the nearest star would typically be several light years away. You could fire a spaceship in a random direction and travel for thousands of years without hitting anything larger than a dust particle. The galaxy is vast and full of stars, but those stars are separated by unimaginable gulfs of nothing. This emptiness is why astronomers do not worry much about the Milky Way and Andromeda colliding. When two galaxies merge, they pass through each other like two clouds of bees. Individual bees might occasionally bump into each other, but mostly they just intermingle. The chance of any two stars actually hitting each other during the galactic collision is essentially zero. What will change during the merger is the structure of the galaxies. The beautiful spiral arms will be disrupted by gravitational interactions. Stars will be flung into new orbits, some ejected from the combined galaxy entirely. gas clouds will compress and trigger bursts of star formation. The orderly dance of the disk will give way to a chaotic scramble as the galaxies settle into their new combined form. Let us now explore more deeply what lies between the stars. Interstellar space is not a perfect vacuum. It contains gas and dust, spread incredibly thin but present throughout the galaxy. This interstellar medium is the raw material from which new stars form and the graveyard of old stars that have ended their lives. The average density of the interstellar medium is about 1 atom per cubic centimeter. Compare this to the air you are breathing, which contains about 10 to the 19th power molecules per cubic centimeter. The interstellar medium is roughly 10 quintillion times less dense than the air around you. This is far more empty than any vacuum we can create in a laboratory on Earth. Yet even at this incredibly low density, the interstellar medium adds up to a significant amount of mass over galactic distances. Perhaps 10 to 15% of the visible mass of the Milky Way is in the form of gas and dust between the stars. This material is crucial for the ongoing life of the galaxy, providing the fuel for new generations of stars. The interstellar medium is not uniform. It clumps into clouds of various sizes and densities, separated by regions of even more sparse material. Some clouds are cold and dense, only 10 degrees above absolute zero, and containing thousands of atoms per cubic centimeter. These molecular clouds are the stellar nurseries where new stars are born. Other regions are hot and thin, heated by radiation from nearby stars to millions of degrees, but containing only a fraction of an atom per cubic centimeter. Giant molecular clouds are the largest structures in the interstellar medium. They can span hundreds of light years across and contain millions of times the mass of the Sun. Deep within these clouds, gravity slowly pulls material together. Knots of gas contract and heat up, eventually becoming dense and hot enough to ignite nuclear fusion. A new star is born, adding its light to the galaxy. The Orion Nebula is a famous stellar nursery visible even to the naked eye as a fuzzy spot in the sword of the constellation Orion. It lies about 1,300 light-years from Earth and contains hundreds of young stars that formed within the past few million years. When you look at the Orion Nebula, you are watching star formation in action, seeing the process that created our Sun almost 5 billion years ago. Star formation does not happen everywhere in the galaxy at the same rate. It is concentrated in the spiral arms, where gas is compressed by the passage of density waves. The bright blue color of the spiral arms in photographs comes from hot young stars that have recently formed there. Older stars spread out between the arms, but new stars are continually being created in these denser regions. The Milky Way forms new stars at a rate of about 1 to 3 solar masses per year. That means material equivalent to 1 to 3 suns is converted from gas into new stars every year. This might not sound like much, but over billions of years it adds up. Most of the stars we see today were formed over the long history of the galaxy, generation after generation of new stars joining the cosmic dance. But stars do not live forever. Every star eventually exhausts its nuclear fuel and dies. The manner of death depends on the mass of the star. Low-mass stars like our Sun will swell into red giants before gently shedding their outer layers and fading into white dwarfs. High-mass stars explode as supernovae, briefly outshining entire galaxies before leaving behind neutron stars or black holes. Our Sun has about 5 billion years of fuel left. It has been burning hydrogen in its core for about 4.5 billion years and will continue for another 5 billion. When the hydrogen runs out, the Sun will begin fusing helium. swelling into a red giant that will engulf Mercury and Venus and possibly Earth. Eventually, the outer layers will drift away, forming a beautiful planetary nebula around the remaining white dwarf core. Supernovae are among the most violent events in the universe. A massive star, at least 8 times the mass of the Sun, can collapse in seconds, releasing more energy than the Sun will produce in its entire lifetime. The explosion flings heavy elements into space, seeding the interstellar medium with the raw materials for new stars and planets. Without supernovae, the universe would contain only hydrogen and helium, and life as we know it could not exist. The Milky Way experiences a supernova roughly once or twice per century. The last one, visible from Earth with the naked eye, occurred in 1604, before the invention of the telescope. Astronomers are eagerly waiting for the next nearby supernova, which will provide an unprecedented opportunity to study these cosmic explosions in detail. Neutron stars are the collapsed cores of massive stars that exploded as supernovae. They pack more mass than the Sun into a sphere only about 20 kilometers across. The matter in a neutron star is compressed to incredible densities, far beyond anything we can create on Earth. A teaspoon of neutron star material would weigh about 1 billion tons. Some neutron stars spin rapidly and emit beams of radiation from their magnetic poles, like cosmic lighthouses. When one of these beams happens to sweep across Earth, we see a pulse of radio waves. These pulses are incredibly precise timekeepers, spinning hundreds of times per second with clockwork regularity. They are used by astronomers as tools for testing physics and detecting gravitational waves. Black holes are even more extreme. When a star, more than about 25 times the mass of the Sun, explodes, the core can collapse all the way to a singularity, a point of infinite density where the normal laws of physics break down. Surrounding this singularity is the event horizon, the boundary beyond which nothing can escape, not even light. The Milky Way contains millions of stellar mass black holes, the remnants of massive stars that have died over billions of years. Most of these are invisible, drifting through space and only detectable if they happen to have a companion star from which they can pull material. When gas falls toward a black hole, it heats up and emits X-rays, revealing the black hole's presence. Beyond these stellar mass black holes, there are intermediate mass black holes, ranging from hundreds to tens of thousands of solar masses. These might form from the mergers of smaller black holes, or from the direct collapse of massive gas clouds. Intermediate mass black holes are harder to find than their smaller or larger cousins, and only a few candidates have been identified so far. And then there are the supermassive black holes at the centers of galaxies. Sagittarius A star, our own central black hole, contains about 4 million solar masses. The largest known supermassive black holes contain tens of billions of solar masses, monsters beyond comprehension that dominate the centers of the largest galaxies in the universe. How supermassive black holes form is one of the great mysteries of modern astronomy. They seem to have existed since very early in the history of the universe, appearing in galaxies when the cosmos was less than 1 billion years old. It is not clear how they could have grown so large so quickly. Perhaps they started from the collapse of massive primordial gas clouds, or perhaps they grew from the mergers of many smaller black holes. The answer remains elusive. The diversity of stars in the Milky Way is staggering. Our galaxy contains stars ranging from tiny red dwarfs, barely large enough to sustain nuclear fusion, to massive blue giants hundreds of times the mass of the Sun. Each type of star has its own lifespan, its own characteristics, and its own fate. Red dwarfs are the most common stars in the galaxy. They are small and cool, glowing with a dim red light that makes them difficult to see from great distances. But they are incredibly long-lived. A red dwarf can burn its hydrogen fuel for trillions of years, far longer than the current age of the universe. Every red dwarf that has ever formed is still shining today, and they will continue to shine for vast stretches of cosmic time. Our Sun is a yellow dwarf, a medium-sized star that glows with a yellowish-white light. It is larger and brighter than a red dwarf, but smaller and cooler than the massive blue stars. Yellow dwarfs live for about 10 billion years, making them stable enough for planets to develop life, but not so long-lived that they will outlast the universe itself. Blue giant stars are the hot rods of the stellar world. They are massive and bright, burning through their fuel at prodigious rates. A blue giant might be hundreds of thousands of times more luminous than the Sun, visible from vast distances across the galaxy. But this brilliance comes at a cost. Blue giants live only a few million years before exhausting their fuel and exploding as supernovae. The color of a star tells us its temperature. Red stars are the coolest, with surface temperatures around 3,000 degrees. Yellow stars like our Sun are medium temperature, around 5,000 to 6,000 degrees. Blue and white stars are the hottest, with surface temperatures exceeding 20,000 degrees. All of these temperatures are hot by human standards, but the differences between them determine the star's behavior and fate. The Hertzsprung-Russell diagram is a fundamental tool astronomers use to classify stars. It plots stellar luminosity against surface temperature, revealing patterns in how stars behave. Most stars fall along a diagonal band called the main sequence, where they spend most of their lives burning hydrogen in their cores. When stars exhaust their core hydrogen, they leave the main sequence and evolve into giants or supergiants before eventually dying. Binary star systems are extremely common in the Milky Way. Perhaps half or more of all stars have at least one companion star, orbiting around a common center of mass. Some binaries are so close that material flows from one star to the other. Others are so far apart that they barely influence each other at all. Triple and quadruple star systems exist as well. Complex gravitational dances performed over millions of years. Binary stars are more than just cosmic curiosities. They allow astronomers to measure stellar masses directly by watching how the stars orbit each other. They can produce spectacular phenomena like nova explosions, when material from one star falls onto a white dwarf companion. And they are the source of some of the most energetic events in the universe, when two compact objects spiral together and merge. The detection of gravitational waves has opened a new window on the universe. When massive objects accelerate, they create ripples in the fabric of space-time that spread outward at the speed of light. These gravitational waves are incredibly weak by the time they reach Earth, but sensitive detectors can pick them up. In 2015, gravitational waves from the merger of two black holes were detected for the first time, confirming a prediction Einstein made a century earlier. Since then, dozens of gravitational wave events have been recorded. We have heard the cosmic chirps of merging black holes and the longer signals from colliding neutron stars. These observations are teaching us about the populations of compact objects in the universe and providing new tests of gravity under extreme conditions. Gravitational wave astronomy is still in its infancy, but it promises to reveal secrets of the cosmos that light alone cannot tell us. The stars of the Milky Way are not randomly distributed. They organize themselves into structures that reflect the galaxy's history and dynamics. The younger stars are found in the thin disk, concentrated in the spiral arms, where star formation is most active. Older stars populate a thicker disk and the central bulge. The oldest stars of all are scattered through the halo, remnants of the early days of galactic assembly. These different populations of stars have different chemical compositions. The oldest stars, those in the halo and globular clusters, contain very few elements heavier than helium. They formed before generations of stellar death had enriched the universe with heavy elements. Younger stars, including our Sun, contain more heavy elements, the accumulated products of billions of years of stellar nucleosynthesis. Astronomers measure the chemical composition of stars to determine their ages and trace the history of the galaxy. A star's spectrum reveals which elements it contains and in what proportions. By studying thousands of stars across the galaxy, scientists can piece together the story of how the Milky Way formed and evolved over cosmic time. The story of the Milky Way begins shortly after the Big Bang itself. In the first few 100 million years of cosmic history, the universe was filled with hydrogen and helium gas, the products of the primordial fireball. There were no stars yet, no galaxies, just vast clouds of gas expanding through space. Gravity began to work on these clouds. Small fluctuations in density, tiny regions where the gas was slightly denser than average, became seeds for structure formation. These denser regions pulled in more gas from their surroundings, growing larger and denser over time. Eventually, the first stars ignited, ending the cosmic dark ages and beginning the era of starlight. These first stars were probably massive and short-lived, burning through their fuel quickly and exploding as supernovae. Their explosions seeded the surrounding gas with heavy elements and created shockwaves that triggered more star formation. The cycle of stellar birth and death had begun. At some point in this early era, the proto-Milky Way began to assemble. Dark matter collected into a halo, providing a gravitational framework for the visible matter to follow. Gas fell into this halo and began to form stars. The exact sequence of events is still debated, but by the time the universe was a few billion years old, something recognizable as our galaxy had taken shape. The oldest stars in the Milky Way are about 13 billion years old, formed when the universe itself was less than a billion years old. These ancient stars are found primarily in globular clusters and the galactic halo. They contain almost no elements heavier than hydrogen and helium, because they formed before generations of stellar death had produced those elements. As the galaxy evolved, more and more heavy elements accumulated in the interstellar medium. Each generation of stars was born from material that had been enriched by the deaths of earlier generations. The disk of the galaxy formed and grew as gas continued to fall in and form stars. The spiral structure developed, maintained by the gravitational dynamics of the rotating disk. The Milky Way did not grow in isolation. Over its history, it has absorbed numerous smaller galaxies that wandered too close. Each merger added stars and gas to our galaxy, contributing to its growth. Some of these absorbed galaxies have left detectable traces, streams of stars that still follow the orbits of their former homes. One of the most significant merger events in the Milky Way's history happened about 8 to 11 billion years ago. A dwarf galaxy, now called Gaia Enceladus, or the Gaia Sausage, collided with our galaxy and was torn apart. Its stars were scattered throughout the inner halo of the Milky Way, contributing a substantial fraction of the stars we see in that region today. This was not a gentle encounter. The Gaia Enceladus merger left scars on our galaxy that are still visible today. The distribution of stellar orbits in the inner galaxy shows evidence of this ancient collision. By studying these orbital patterns, astronomers can reconstruct what happened billions of years ago, like archaeologists piecing together the history of an ancient civilization. More recent mergers have also left their marks. The Sagittarius dwarf galaxy, which is currently being torn apart by the Milky Way, represents the next chapter in this ongoing story of galactic cannibalism. The large and small Magellanic Clouds will eventually suffer the same fate, their stars adding to the mass of our ever-growing galaxy. The merger with Andromeda in several billion years will be the most transformative event in the Milky Way's future history. Both galaxies will lose their spiral structure and combine into something new. Our galaxy's story will end, in a sense, replaced by the story of whatever emerges from the collision. Throughout all of this history, planets have been forming around stars. Planetary systems are not rare or special. They appear to be a normal outcome of star formation, arising naturally from the disks of gas and dust that surround young stars. The discovery of exoplanets, planets around other stars, has revolutionized our understanding of planetary systems and our place in the cosmos. The first exoplanets were discovered in the early 1990s, and since then, thousands more have been found. Some are gas giants like Jupiter, orbiting close to their stars in configurations very different from our solar system. Others are small rocky worlds that might bear some resemblance to Earth. A few orbit in the habitable zones of their stars, where liquid water could potentially exist on their surfaces. The Kepler Space Telescope was particularly transformative for exoplanet science. By staring at a single patch of sky for years, it detected the tiny dimming of stars as planets passed in front of them. Kepler found that planets are incredibly common, that most stars have at least one planet, and that small rocky planets are more common than gas giants. Based on Kepler's results, astronomers estimate that the Milky Way contains hundreds of billions of planets. That is roughly one planet for every star on average, though the distribution varies. Some stars have elaborate systems with many planets, while others appear to have none. But the total number of planets in our galaxy is staggering. Among these hundreds of billions of planets, how many might support life? This is one of the most profound questions humanity has ever asked, and we do not yet have the answer. But we can make some educated guesses based on what we know about the conditions life needs. Life as we know it requires liquid water, a source of energy, and certain chemical elements. Rocky planets in the habitable zones of their stars might have liquid water on their surfaces. Stars provide energy through their light, and the heavy elements needed for life are scattered throughout the galaxy, produced by generations of stellar evolution. Conservative estimates suggest there might be tens of billions of potentially habitable planets in the Milky Way. These are rocky planets, roughly Earth-sized, orbiting in the habitable zones of their stars. Not all of them would actually be habitable, of course. Many factors determine whether a planet can support life, and we understand only a few of them. But even if only a tiny fraction of these potentially habitable planets actually developed life, the numbers would still be enormous. If 1 in a million habitable planets hosts life, that would mean tens of thousands of living worlds in our galaxy alone. If the fraction is higher, the number could be in the millions. We have not yet detected life on any world beyond Earth, but we have barely begun to look. Our current technology can detect the presence of planets around other stars, but studying those planets in detail remains extremely difficult. We cannot yet determine whether an exoplanet has an atmosphere, much less whether that atmosphere contains signs of life. Future telescopes and missions will change this. The James Webb Space Telescope can analyze the atmospheres of some exoplanets, looking for gases that might indicate biological activity. Proposed future missions could go even further, searching for specific biosignatures in the light from other worlds. Within a few decades, we might have our first evidence of life beyond Earth. The implications of finding life elsewhere would be profound. It would tell us that life is not unique to Earth, that the universe can generate living things more than once. It might provide insights into how life originates and evolves, and it would forever change our sense of our place in the cosmos. The search for intelligent life is even more speculative, but no less fascinating. The Drake equation attempts to estimate the number of communicating civilizations in the galaxy by multiplying together various factors, from the rate of star formation to the fraction of civilizations that develop radio technology. The answers range from essentially 0 to millions, depending on what values you plug in for the unknown factors. The Fermi paradox asks a simple question. If intelligent life is common in the galaxy, where is everyone? We have detected no unambiguous signals from alien civilizations, no visitors, no evidence of galactic engineering projects. The galaxy is 13 billion years old, plenty of time for intelligent species to spread across its entire width. Yet we see no evidence of this. Many explanations for the Fermi paradox have been proposed. Perhaps intelligent life is much rarer than we think, and we are effectively alone. Perhaps civilizations tend to destroy themselves before they can spread to the stars. Perhaps they exist, but are not communicating in ways we can detect. Perhaps they are simply too far away for us to notice yet. The answer, whatever it turns out to be, will tell us something important about the nature of intelligence and the fate of civilizations. Our exploration of the Milky Way has so far been limited to our immediate cosmic neighborhood. We have sent spacecraft to every planet in our solar system and landed probes on several of them. We have studied the Sun from close range and sent a probe hurtling out of the solar system entirely. But we have not yet sent anything to another star. The distances are simply too vast for our current technology. Even traveling at the speed of the fastest spacecraft we have ever built, it would take tens of thousands of years to reach the nearest star. No one can wait that long for results. To explore the galaxy directly, we would need breakthroughs in propulsion technology that are still science fiction. Yet some scientists are thinking about how interstellar travel might be possible. Projects like Breakthrough Starshot aim to send tiny probes to nearby stars using powerful lasers to accelerate them to a significant fraction of the speed of light. At 20% of light speed, a probe could reach Alpha Centauri in about 20 years, a journey that might be completed within a human lifetime. These probes would be small and simple, unable to do much more than take pictures as they fly past their targets. But they would represent humanity's first direct exploration beyond the solar system, our first physical presence around another star. The data they return could reveal details about nearby planetary systems that we cannot observe from Earth. More ambitious visions imagine crewed starships carrying colonists to other worlds. Such ships would need to sustain human life for decades or centuries, providing food, water, air, and living space for generations of travelers. The engineering challenges are immense, and the cost would be astronomical. But nothing in physics prevents such ships from being built. If humanity ever becomes an interstellar species, spreading from star to star across the galaxy, we would join whatever other civilizations might already be out there. We would become part of the galactic community, if such a community exists. The Milky Way would become not just our home, but our habitat, a galaxy populated by Earth life wherever we manage to spread. Or perhaps we will remain confined to our solar system, limited by distance and the finite lifespans of our spacecraft and ourselves. Perhaps we will study the galaxy through ever more powerful telescopes without ever visiting it in person. This too would be a worthy fate, to become a species that knows its cosmic home intimately, even if it never leaves its cradle. The choice, to the extent we have one, lies with future generations. They will decide whether to stay or to go, whether to reach for the stars or to tend our garden here at home. What we can give them is knowledge, an understanding of the cosmos that makes informed choices possible. That is what science provides, not just facts about distant objects, but a framework for making decisions about our future. Every photograph of a distant galaxy, every map of the cosmic microwave background, every detection of an exoplanet adds to this storehouse of knowledge. We are still in the early stages of understanding our galaxy and our universe, but we have come an astonishingly long way in just a few centuries, from thinking the stars were pinpricks in a celestial sphere to mapping the structure of the cosmos across billions of light years. The pace of discovery shows no signs of slowing. New telescopes and instruments come online regularly, each revealing details that previous generations could not see. Gravitational wave detectors open new senses for experiencing the universe. Computer simulations grow more sophisticated, allowing us to model the formation of galaxies and the evolution of cosmic structure. The golden age of astronomy is not behind us. It is now, and it will continue into the future. Perhaps the most remarkable thing about all of this is that we can understand it at all. The laws of physics that govern the behavior of atoms in a laboratory also govern the behavior of stars and galaxies across the universe. The same mathematics that describes the motion of a falling apple also describes the orbits of planets around distant suns. The universe is comprehensible, at least in part, and we are the species that figured this out. This comprehension is itself a kind of miracle. Evolution shaped our brains to survive on the African savanna, to find food and avoid predators and raise children. Nothing in that evolutionary history would seem to prepare us for understanding quantum mechanics or general relativity. Yet here we are, probing the deepest secrets of the cosmos from a small planet orbiting an unremarkable star. The Milky Way does not know we are here. It is not aware of us, any more than it is aware of any other collection of atoms within its spiral arms. But we are aware of it. We have named it and mapped it and studied it. We have learned its size and its shape and its composition. We have traced its history and predicted its future. In some sense, we are the galaxy looking back at itself, a piece of the cosmos that has become conscious. This consciousness carries with it responsibility. We are the only creatures we know of who can understand what the Milky Way is and where it is going. We are the only ones who can appreciate its beauty and its terror, its vastness and its age. If we destroy ourselves through war or environmental catastrophe, that understanding would be lost. The galaxy would continue to turn, but there might be no one left to marvel at it. Perhaps there are other minds out there, other species on other worlds who have also awakened to the reality of the cosmos. Perhaps they too have mapped their galaxy and wondered about their place in it. If so, we are not alone in our wonder, even if we have not yet found our cosmic neighbors. The universe might be full of consciousness, scattered across billions of planets around trillions of stars. Or perhaps we are alone. Perhaps Earth is the only world where atoms have arranged themselves into structures capable of asking where they came from. In that case, our responsibility is even greater. We would be the sole repository of cosmic awareness, the only eyes through which the universe can see itself. To let that light go out through negligence or foolishness would be the greatest tragedy imaginable. We do not know which of these scenarios is true. We do not know if the galaxy teems with life, or if we are its only representatives. The answer will not change the beauty of the Milky Way or diminish the wonder of its scale, but it will change how we see ourselves, how we understand our role in the vast cosmic drama that has been unfolding for billions of years. Let us take a moment to consider what it means to look across the galaxy. When you gaze at a star that is 10,000 light years away, you are seeing that star as it was 10,000 years ago. The light entering your eyes began its journey when humans were just learning to farm and build permanent settlements. The star itself has moved since then, changed since then, perhaps even died since then. You are looking at a ghost, an image from an ancient past. This effect of looking back in time becomes even more dramatic when we look at distant galaxies. The Andromeda galaxy is 2.5 million light years away. When you see Andromeda in the night sky, you are seeing it as it was when our distant ancestors were first beginning to walk upright. The light from the most distant galaxies we can observe has been traveling for more than 13 billion years, showing us the universe as it was when galaxies were just beginning to form. In a very real sense, astronomers are historians. We cannot travel to the past, but we can look at it. The universe has provided us with a time machine of sorts, one that lets us see how things were eons ago, simply by looking far enough away. The farther we look, the deeper into history we see. The cosmic microwave background shows us the universe at an age of just 380,000 years, a baby picture of the cosmos. This connection between distance and time means that the universe we observe is not a snapshot of a single moment. It is a composite image, layers of different eras stacked on top of each other. Nearby stars show us the recent past. Distant galaxies show us the ancient past. The cosmic microwave background shows us the earliest era we can observe directly. We see all of these eras simultaneously, a time-lapse photograph of cosmic history. The speed of light is not just a universal speed limit. It is also the speed of causality, the fastest rate at which any influence can propagate through space. Nothing can travel faster than light. No information can be transmitted faster than light, and no effect can precede its cause by traveling faster than light. This fundamental limit shapes everything about the universe we observe. Einstein's theory of relativity tells us that space and time are not separate things, but aspects of a single unified entity called space-time. Massive objects curve space-time around them, and this curvature is what we experience as gravity. Light follows the curves of space-time, bending around massive objects. Time itself runs slower in stronger gravitational fields, a prediction that has been confirmed by countless experiments. The curvature of space-time around Sagittarius A star is extreme. Near the event horizon of this supermassive black hole, space-time is so warped that the normal rules of geometry break down. Time runs dramatically slower there than it does out here in the galactic suburbs. If you could somehow survive a trip near the black hole and return, you would find that centuries had passed back home, while only years had passed for you. Black holes are among the most extreme predictions of general relativity, and for decades many physicists doubted they could actually exist. But the evidence has mounted to the point where their reality is no longer in question. We have detected gravitational waves from merging black holes. We have imaged the shadow of Sagittarius A star and the supermassive black hole in the galaxy M87. We have watched stars orbit around invisible massive objects at the centers of galaxies. Black holes are real, and they are common. The interior of a black hole is beyond our ability to observe directly. Once something crosses the event horizon, it is cut off from the rest of the universe. No light can escape, no signal can be sent. Whatever happens inside remains hidden forever. Theories suggest that space-time inside a black hole is warped into strange configurations, perhaps containing wormholes to other parts of the universe, or even to other universes entirely. But we have no way to test these ideas. Wormholes are theoretical passages through space-time that could connect distant points in space or time. They arise naturally from the mathematics of general relativity, but require exotic matter with negative energy density to remain open. We have never detected such matter, and we do not know if it can exist. Wormholes remain firmly in the realm of speculation, fascinating possibilities that may never be realized. Time travel is another consequence of general relativity that excites the imagination. Certain solutions to Einstein's equations allow for closed time-like curves, paths through space-time that loop back on themselves and return to their starting point. An object following such a path could potentially meet its past self. But the conditions required for such paths to exist are extreme, and it is not clear whether they can occur in the real universe. Most physicists believe that time travel to the past is impossible, despite what the equations seem to allow. The paradoxes it would create, like going back in time and preventing your own birth, suggest that some principle of nature forbids it. Stephen Hawking proposed a chronology protection conjecture, suggesting that the laws of physics conspire to prevent time travel to the past. But we do not yet have a complete theory that proves this. Time travel to the future, on the other hand, is definitely possible. We do it all the time. You are traveling into the future right now at a rate of 1 second per second. Relativity tells us that you can travel into the future faster by moving at high speeds or by spending time in strong gravitational fields. Astronauts on the International Space Station age slightly slower than people on Earth, though the difference is tiny. For more dramatic time dilation, you would need to travel at speeds approaching the speed of light or visit environments with much stronger gravity. Spending time near a black hole would send you into the far future of the outside universe. Traveling on a spaceship at 99% the speed of light would cause years to pass on Earth for every few months you experienced. These are not science fiction scenarios, but real consequences of the physics we already understand. The structure of space-time across the Milky Way is mostly gentle. Away from stellar remnants like white dwarfs, neutron stars, and black holes, space-time is nearly flat. The sun's gravity curves space-time slightly, enough to bend light from distant stars and cause Mercury's orbit to precess. But the effects are small compared to what happens near the extreme objects that pepper the galaxy. Let us now explore some specific regions of the Milky Way in more detail. We have talked about the overall structure, but the galaxy contains countless individual objects and regions that deserve attention. Each one tells a part of the larger story of our cosmic home. The galactic center is one of the most extreme environments in the Milky Way. Within the central few light years around Sagittarius, a star, stars are packed thousands of times more densely than in our neighborhood. They zip around the central black hole at thousands of kilometers per second. Supernovae have exploded there, and massive stars continue to form despite the hostile conditions. One of the most spectacular features near the galactic center is the Arches cluster, the densest known star cluster in the Milky Way. It contains about 150 young, hot, massive stars packed into a region less than 1 light-year across. These stars are so bright that if the Arches cluster were as close to Earth as the nearest star, they would be visible in broad daylight. The galactic center is shrouded in dust and gas that blocks visible light. We cannot see it with our eyes, even on the darkest night, but infrared and radio waves pass through the dust, allowing astronomers to study this region in detail. The images reveal a turbulent environment with streamers of gas, violent stellar winds, and the ever-present gravitational influence of the central black hole. Moving outward from the center, we enter the galactic bar, the elongated structure that stretches across the inner part of the Milky Way. The bar channels gas toward the center and influences the orbits of billions of stars. It rotates as a solid body, maintaining its shape as the inner galaxy turns. Beyond the bar lie the spiral arms, the most visually striking features of our galaxy. The arms are not solid structures but density waves, ripples in the distribution of matter that propagate through the disk. As gas passes through these denser regions, it gets compressed and forms new stars. The young hot stars light up the arms, making them visible from across the universe. The Perseus arm is one of the 2 major spiral arms of the Milky Way. It sweeps around the outer part of the galaxy, containing many star-forming regions and young stellar clusters. The California Nebula, a vast cloud of glowing gas illuminated by a nearby hot star, lies in the Perseus arm about 1,000 light-years from Earth. The Sagittarius arm lies closer to the galactic center than our location. It contains the Eagle Nebula, famous for its pillars of creation photographed by the Hubble Space Telescope. These pillars are columns of gas and dust where new stars are forming, silhouetted against the glowing background of the nebula. The image has become one of the most iconic photographs in astronomy. Our own Orion arm, sometimes called the Orion Spur, lies between the Sagittarius and Perseus arms. It is a minor arm segment rather than a major spiral arm, but it contains our solar system and many familiar celestial objects. The Orion Nebula, the Pleiades star cluster, and the bright star Betelgeuse are all part of our local arm. The outer reaches of the Milky Way are less well studied than the inner regions. Stars thin out as you move away from the galactic center, and the spiral structure becomes less distinct. But the disk continues far beyond our position, extending perhaps 200,000 light-years from center to edge. Stars at the outer edge orbit slowly, taking billions of years to complete a single circuit of the galaxy. Beyond the disk lies the halo, populated by old stars and globular clusters on highly elliptical orbits. Omega Centauri is the largest globular cluster associated with the Milky Way, containing about 10 million stars packed into a sphere roughly 150 light-years across. It is so large that some astronomers believe it might be the stripped core of a dwarf galaxy that was absorbed by the Milky Way long ago. The globular cluster 47 Tucani is another spectacular example. Visible to the naked eye from the southern hemisphere as a fuzzy star, it contains several million stars, including some of the oldest in the galaxy. Studying globular clusters gives us insight into the early universe, when these ancient stellar cities formed. The halo extends far beyond the disk, perhaps 600,000 light-years from the galactic center. Most of this volume is dark matter, invisible but detectable through its gravitational influence. The stars in the halo are spread thinly, isolated wanderers on journeys that take them far from the crowded galactic plane. Some halo stars have been ejected from the galaxy entirely, These hypervelocity stars are moving so fast that they will escape the Milky Way's gravity and fly off into intergalactic space. They were probably accelerated by close encounters with the central supermassive black hole, flung outward at speeds exceeding 1,000,000 kilometers per hour. The space between galaxies is not entirely empty. Intergalactic space contains extremely thin gas, perhaps 1 atom per cubic meter on average. It also contains dark matter, distributed throughout the cosmic web that connects galaxies. And it contains the occasional star, ejected from galaxies and wandering through the void. These intergalactic wanderers are truly alone. They have no neighboring stars for millions of light years. If planets orbit them, those planets would see a night sky almost entirely dark, with only the faint smudges of distant galaxies visible. The loneliness would be complete, a single point of light in an ocean of blackness. The Milky Way is surrounded by a population of these wandering stars, along with the dwarf galaxies and stellar streams that orbit in the halo. Studying this extended structure tells us about the formation history of our galaxy and its interactions with its neighbors. The halo is a fossil record, preserving evidence of ancient events that shaped the Milky Way we see today. As we contemplate all of this structure, from the crowded galactic center to the lonely intergalactic voids, a sense of scale begins to emerge. The Milky Way is not just a collection of stars. It is an ecosystem, a vast system of interacting components that has evolved over billions of years. Stars are born, live, and die, enriching the galaxy with heavy elements. Gas flows in and out, accreting from the cosmic web and being expelled by supernovae. Dark matter provides the gravitational scaffolding that holds it all together. We are part of this ecosystem. The atoms in our bodies were forged in this galaxy, cycled through multiple generations of stars before ending up on Earth. We breathe air that contains oxygen made by stellar fusion. We are nourished by carbon-based molecules that could only exist because stars created those atoms and scattered them through space. Our very existence is a product of galactic evolution, and now we have become aware of this connection. Through science, we have traced our origins back through the history of the galaxy. We have learned where our atoms came from and how they got here. We have discovered that we are not separate from the cosmos, but intimately connected to it. We are the Milky Way contemplating itself. This contemplation brings with it a kind of responsibility. We are not just inhabitants of the galaxy, but its observers, its documenters, perhaps its only witnesses who can understand what they are seeing. The galaxy does not need us to exist. It was here for billions of years before life arose on Earth, and will continue for billions more after we are gone. But while we are here, we can appreciate it in ways that no unconscious process ever could. The future of the Milky Way stretches out before us like an endless cosmic highway. Over the next few billion years, our galaxy will continue to evolve, its spiral arms turning slowly around the center, new stars being born, while old stars die. The fundamental processes that have shaped the galaxy for 13 billion years will continue, transforming it in ways both predictable and surprising. In the near term, cosmically speaking, the most dramatic event will be the collision with Andromeda. As we discussed earlier, this merger is inevitable. The two great spiral galaxies of the local group are falling toward each other, pulled by their mutual gravity across the void between them. In about 4 billion years, they will begin their first close passage. Computer simulations have shown us what this collision will look like. As the galaxies approach, tidal forces will begin to distort their shapes. Long streamers of stars will be pulled out from each galaxy, forming cosmic bridges between them. The spiral arms will begin to unwind as the orderly rotations are disrupted by the gravitational chaos of the encounter. The first passage will not be the end. After passing through each other, the galaxies will separate again, their momentum carrying them apart. But they will not escape. Gravity will slow their separation and pull them back together for a second encounter, then a third, then more. Each passage will bring more mixing, more distortion, more transformation. Eventually, after perhaps 1 billion years of this cosmic dance, the two galaxies will fully merge. The combined system will settle into a new configuration, probably an elliptical galaxy without spiral arms. The beautiful spiral structure that we admire today will be gone, replaced by a smooth, featureless blob of stars. This merged galaxy, which we might call Milky, will contain the combined stars of both parent galaxies, roughly 1 trillion stars in total. Many of those stars will have been flung into new orbits during the merger, redistributed throughout the new galaxy. Some will have been ejected entirely, sent flying into intergalactic space never to return. Our own solar system will probably survive the merger. The distances between stars are so vast that actual collisions are extremely unlikely, but our orbit around the galactic center will certainly change. We might be flung far from our current position, perhaps into the outer reaches of the new galaxy, or we might fall toward the center, finding ourselves in a denser stellar environment than we know today. By the time this merger happens, Earth will already be gone. In about 5 billion years, the Sun will exhaust its hydrogen fuel and swell into a red giant. Its outer layers will expand past the orbit of Venus and possibly engulf Earth. Even if Earth survives this engulfment, its surface will be scorched and sterilized, any remaining water boiled away into space. The Sun will then shed its outer layers, forming a planetary nebula that will shine briefly before fading away. What remains will be a white dwarf, a dense stellar remnant about the size of Earth but containing most of the Sun's mass. This white dwarf will slowly cool over billions of years, eventually fading to a black dwarf, a cold dark cinder drifting through the galaxy. This fate awaits most of the stars in the Milky Way. The majority of stars are small and long-lived, but eventually even they will run out of fuel. One by one, over trillions of years, the stars will wink out, leaving behind white dwarfs that gradually cool and fade. The very largest stars will have different fates. They will explode as supernovae, leaving behind neutron stars or black holes. These compact remnants will persist for incredibly long times, though even they are not eternal. Neutron stars will eventually cool to the point where they can no longer be detected. Black holes will slowly evaporate through a process called Hawking radiation, though this takes an almost inconceivably long time. The stellar black holes in the Milky Way will take roughly 10 to the 67th power years to evaporate, a number so large that it dwarfs the current age of the universe by an unimaginable factor. The supermassive black holes at the centers of galaxies will take even longer, perhaps 10 to the 100th power years. These are timescales that stretch the limits of human comprehension. But eventually, even the black holes will be gone. At that point, countless trillions of years in the future, the universe will be a cold, dark, empty place. No stars will shine. No planets will orbit. No processes will generate heat or light. The universe will have reached its final state, a condition sometimes called heat death. This is the ultimate fate of the Milky Way and of the entire cosmos. The relentless increase of entropy, the tendency for concentrated energy to spread out and dissipate, will eventually win. all the structure we see today, the galaxies and stars and planets, all of it is temporary. Given enough time, it will all dissolve into a thin, uniform soup of particles, barely warmer than absolute zero. But we should not be dismayed by this distant future. The timescales involved are so enormous that they exceed any meaningful comparison with human experience. Trillions of years is not just a long time. It is an eternity compared to the lifetime of any individual or any civilization. The heat death of the universe is not something to worry about. It is simply the ultimate context for everything that happens before it, and so much will happen before it. The universe is currently about 14 billion years old, but it will continue to produce stars for perhaps another 100 trillion years. That is 7,000 times longer than it has already existed. The age of stars is just beginning. We are living in the cosmic morning, not the cosmic evening. During that vast stretch of stellar time, countless civilizations might rise and fall across the galaxies. Intelligence might spread through the cosmos, colonizing star systems and engineering worlds, or it might remain rare, isolated sparks of awareness in a mostly mindless universe. Either way, the opportunities for complexity and beauty and meaning are almost limitless. Consider what life might accomplish in 100 trillion years. If intelligence survives the death of its home stars, it could spread across galaxies, capturing the energy of billions of suns. It could create structures on scales that dwarf anything we can currently imagine. It could witness the slow winding down of the cosmos, documenting the final eras of the universe as carefully as we document the earliest. Some futurists have speculated about civilizations that could survive even the death of the stars, by harvesting the rotational energy of black holes, or by exploiting subtle quantum effects. Extremely advanced beings might eke out an existence even in the cold darkness after the last star has faded. Life finds a way, as the saying goes, and perhaps it will find ways we cannot yet conceive. But let us return to the present, to the Milky Way as it exists today. We have explored its structure from the smallest scales, the asteroids and comets of our solar system, to the largest, the superclusters and cosmic webs that connect galaxies across billions of light years. We have traced its history from the first stars to the eventual merger with Andromeda. We have contemplated its future through the death of the stars and beyond. What does all of this mean for us here on Earth, in this brief moment of cosmic time? Perhaps the most important lesson is one of perspective. The problems that consume our daily lives, the conflicts and concerns that seem so urgent, are vanishingly small when viewed against the backdrop of the cosmos. This does not make them unimportant, but it does put them in context. At the same time, the immensity of the universe does not diminish the significance of our existence. We are the products of billions of years of cosmic evolution, the inheritors of a chain of events stretching back to the Big Bang itself. The atoms in our bodies were forged in the hearts of ancient stars. We are the universe experiencing itself, aware and wondering. This awareness is precious precisely because it may be rare. We do not know how common life is in the cosmos, or how common intelligence. For all we know, we might be alone in the Milky Way, the only eyes that have ever gazed up at these particular stars. Even if we are not alone, even if the galaxy teems with life, our particular perspective is unique. No one else sees the universe exactly as we do. The knowledge we have gained about the Milky Way is one of humanity's greatest achievements. It represents the cumulative work of thousands of scientists over hundreds of years, building on each other's discoveries to create an ever more complete picture of our cosmic home. From Galileo first turning a telescope to the sky, to the latest observations from space-based observatories, Each generation has added to our understanding. This progress shows no signs of stopping. New telescopes and instruments are being developed that will reveal details of the universe we cannot yet see. Gravitational wave observatories will detect the mergers of black holes across the cosmos. Space missions will probe the surfaces of other worlds and perhaps find evidence of life. The 21st century may see discoveries that transform our understanding of our place in the universe. But even with all we have learned, mysteries remain. We do not know what dark matter is, despite its dominance of the galaxy's mass. We do not know what dark energy is, despite its control of cosmic expansion. We do not know whether life exists elsewhere in the Milky Way, despite the billions of potentially habitable planets. These questions await future generations of explorers and scientists. The Milky Way is our home in the deepest sense of that word. It is not just where we live, but what we are made of. We are children of this galaxy, born from its stars, and destined to return our atoms to its interstellar medium when we die. The calcium in our bones, the iron in our blood, the oxygen in our lungs, all of it was forged by nuclear fusion in stellar cores, or created in the violent explosions of dying stars. When ancient humans looked up at the band of light crossing the night sky, they could not have imagined what they were seeing. They did not know that those countless points of light were other suns, many far larger and brighter than our own. They did not know that vast clouds of gas and dust lay between the stars, or that a supermassive black hole lurked at the center. They saw only the pale glow and wondered. Today we have answers to many of their questions, but our wonder has only grown. Each new discovery reveals new mysteries. Each answer raises new questions. The more we learn about the Milky Way, the more we realize how much there is left to learn. The galaxy is not a problem to be solved, but a realm to be explored, a territory that will never be fully mapped. And perhaps that is as it should be. A universe that could be completely understood by a species that evolved to survive on one planet seems unlikely. We were not designed to comprehend the cosmos. The fact that we can comprehend as much as we do is remarkable. Evolution gave us brains that can do physics and mathematics, even though nothing in our evolutionary history required such abilities. We are fortunate beyond measure. Let us cherish this fortune. Let us continue to explore and discover, to push the boundaries of knowledge outward into the unknown. Let us share what we learn with each other and with future generations, building a legacy of understanding that will long outlast any individual. The Milky Way is vast, but so is human curiosity. Together, they make a combination that can achieve almost anything. Every child who looks up at the stars and wonders is continuing a tradition that stretches back to the dawn of human consciousness. Every scientist who analyzes data from a distant observatory is adding a line to a story that began when the first humans noticed patterns in the sky. We are all part of this great enterprise, this endless quest to understand where we are and who we are. The Milky Way will continue to turn whether we study it or not. The stars will burn and die, new stars will form, and the slow dance of cosmic evolution will proceed. But with our awareness, something new has entered the picture. For the first time in the history of the galaxy, a part of it has become conscious of the whole. We are the Milky Way looking back at itself. This perspective is transformative. It changes how we see ourselves and our place in the cosmos. We are not just inhabitants of Earth, but citizens of the galaxy, made of galactic matter and participating in galactic processes. Our history is galactic history. Our future, whatever it may be, is part of the galactic future. The atoms in your body have traveled across the galaxy, They have been part of stars that burned billions of years ago. They have drifted through interstellar space, accumulated in gas clouds, participated in the formation of new stars. After circuitous journeys spanning cosmic time, they found their way to this solar system, to this planet, to you. You are not separate from the Milky Way. You are the Milky Way, temporally organized into a form that can contemplate its own nature. Think again about the scale of what we have explored. The Milky Way spans 100,000 light-years across, a distance so vast that light itself, the fastest thing in the universe, takes 100,000 years to cross from one side to the other. Within this vast expanse float hundreds of billions of stars, each a nuclear furnace converting hydrogen into helium and flooding space with light and heat. Between those stars lies the interstellar medium, clouds of gas and dust spread so thin that the space between atoms exceeds any vacuum we can create on Earth. Yet even this incredibly sparse material adds up to significant mass when spread across galactic distances. It is the raw material from which new stars will form, the recycled ashes of old stars given new life. Surrounding the visible galaxy is the dark matter halo, an invisible sphere of mysterious material that outweighs all the stars and gas combined. This dark matter provides the gravitational scaffolding that holds the galaxy together, shaping the motions of stars and determining the ultimate fate of everything we can see. At the center of it all sits Sagittarius A star, a supermassive black hole with the mass of 4 million suns, compressed into a region smaller than our solar system. This cosmic monster warps space and time around it, trapping anything that ventures too close within its event horizon. Yet even this behemoth is dwarfed by the galaxy it inhabits, a tiny point at the center of a vast spiral of light. Now, let us attempt something almost impossible. Let us try to truly feel, not just understand, but feel the scale of our cosmic home. Imagine you are an ant standing on a basketball. The basketball is your whole world, a curved surface that extends in every direction as far as you can see. You might spend your entire life exploring this basketball, mapping its surface, understanding its texture. The basketball seems enormous to you, a vast territory that dwarfs your tiny body. Now imagine that someone tells you that your basketball is actually floating on an ocean. This ocean is not just large, it is larger than you can possibly comprehend. If your basketball represents the solar system, then the ocean represents the galaxy. The basketball contains everything you know, everything your ancestors explored, everything that feels real and solid and present. But it is just one droplet in a sea that extends beyond the limits of imagination. But wait, the analogy does not stop there. Imagine that someone tells you there are other oceans too, 2 trillion of them, each containing countless basketballs of their own. These oceans are so far apart that traveling from one to another would take longer than the universe has existed. You are not just an ant on a basketball in an ocean. You are an ant on a basketball in an ocean, in a world of oceans, a cosmos of incomprehensible vastness. This is our situation. We are specks on a pale blue dot, orbiting an unremarkable star in the suburbs of an ordinary spiral galaxy in a universe of 2 trillion galaxies. The scale defies comprehension. It humbles us and exalts us simultaneously. Humbles because we are so small. Exalts because we are capable of knowing this truth. No other species on Earth has this knowledge. The dolphins and the elephants, the crows and the octopuses, none of them know they live in a galaxy. None of them have named the stars or calculated their distances. Only we humans have achieved this feat of understanding. Only we have mapped our cosmic address, from the house of Earth to the neighborhood of the solar system, to the city of the Milky Way, to the country of the local group, to the continent of the Laniakea supercluster. And what is our cosmic address worth? Everything and nothing. Everything because knowledge is valuable in itself, because understanding our place in the universe gives context to all our other endeavors. Nothing because the universe does not care whether we understand it. The stars would burn the same whether or not we measured their temperatures. The galaxies would rotate the same whether or not we calculated their masses. But perhaps that is the wrong way to think about it. Perhaps the value of understanding is not measured by its effect on the universe, but by its effect on us. Knowing where we are changes who we are. It shapes our identities, our philosophies, our sense of what matters and what does not. A person who knows they live in an infinite cosmos sees the world differently than a person who thinks the sky is a solid dome. The ancients looked up and saw gods and monsters painted across the heavens. They saw patterns that told stories, constellations that marked the seasons, omens that predicted the future. The sky was alive with meaning, every star a message from the divine. We have replaced those stories with measurements, those gods with gas giants, those omens with orbital mechanics. Some would say we have lost something in the exchange, but I would argue we have gained more than we have lost. The old stories were beautiful, but they were also wrong. The new understanding is also beautiful, and it has the advantage of being true. There is poetry in the real universe, in the birth of stars from collapsing gas clouds, in the death of massive stars as supernova, in the slow spiral of galaxies merging over billions of years. The poetry of facts is deeper than the poetry of fiction. Consider the remarkable chain of events that led to your existence. Billions of years ago, a cloud of gas in the early Milky Way collapsed under its own gravity. The cloud heated up and ignited nuclear fusion, becoming a first-generation star. This star lived fast and died young, exploding as a supernova and scattering heavy elements into space. Those elements mixed with more gas, collapsed again, formed another star. This process repeated multiple times, each generation adding more heavy elements to the cosmic mix. Eventually, about 5 billion years ago, a cloud enriched by the deaths of countless stars collapsed one more time. It formed our sun and the planets that orbit it, including this one, this rare world, where liquid water flows and complex chemistry happens. On this world, somehow, the chemistry became biology. Simple molecules assembled into more complex ones. Cells emerged, then multicellular organisms, then animals that could think. Through billions of years of evolution, the universe developed the ability to contemplate itself. You are that contemplation. You are the cosmos looking back at its own history. The carbon in your cells was made in a star. The calcium in your bones was made in a star. The iron in your blood was made in a star. Everything that you are, physically speaking, was forged in nuclear fires and scattered across light years of space before coming together on this planet. You are not just in the universe. You are of the universe, made from its substance and participating in its processes. When you look up at the Milky Way on a dark night, you are looking at your extended family. Those distant stars are your relatives, formed from the same interstellar medium, governed by the same laws of physics, part of the same grand cosmic dance. The light traveling from them to you carries information about processes similar to those happening in your own body. We are all made of the same stuff, arranged in different ways. This connection extends beyond the physical. The same processes that created the elements in your body also created the elements in planets around other stars. If life exists elsewhere in the galaxy, it is made from the same cosmic raw materials we are. We share a heritage with any beings that might be out there, a common origin in the nuclear furnaces of ancient stars. Perhaps this is why the search for extraterrestrial life captures our imagination so powerfully. It is not just curiosity about whether we are alone. It is a desire to find our cosmic family, to discover that the universe is capable of generating awareness more than once. If there is other life out there, we are part of a larger story than we ever imagined. And if there is not, if we are truly alone in the Milky Way, or even in the observable universe, then we are more precious than we ever imagined. We would be the sole custodians of cosmic awareness, the only eyes through which the universe has ever seen itself. The responsibility would be overwhelming, but also exhilarating. Either way, whether the cosmos teems with life or we are its only conscious inhabitants, our existence is remarkable. The probability of any particular person existing is so vanishingly small that it approaches zero. The chain of events that led to you specifically, out of all the possible people who might have existed, is so improbable that it seems miraculous. Yet here you are, alive and aware and reading these words. The Milky Way has produced you. 4 billion years of terrestrial evolution, 5 billion years of solar system history, 13 billion years of cosmic development, all of it converging in this moment, in your consciousness, in your awareness of where you are and what you are part of. This is the miracle, not supernatural but natural, not inexplicable but explainable, yet no less wondrous for being comprehensible. What will you do with this awareness? How will you use the brief time you have in this ancient and vast universe? These are questions only you can answer. But perhaps the knowledge of where you are can inform those answers. Perhaps understanding the scale of the cosmos can help you identify what truly matters. From the perspective of the Milky Way, human conflicts and concerns are invisible. Wars and politics, triumphs and tragedies, all of it happens on a scale so small that the galaxy cannot notice. This could be depressing, a reminder of our insignificance, but it could also be liberating. The things that cause us stress and suffering are cosmically tiny. They exist at our scale, not at the scale of galaxies and light years. At the same time, the things we cherish are also cosmic in origin. Love and friendship, art and science, joy and wonder. All of these emerge from brains that emerge from evolution, that emerge from chemistry, that emerge from physics, that emerge from the Big Bang. Our experiences, however small, are authentic products of the same universe that produced the Milky Way. We are not separate from the cosmos. Our lives are part of its story. The journey we have taken together is almost complete. We have traveled from the surface of Earth to the edge of the observable universe and back again. We have explored the structure of our solar system, the anatomy of our galaxy, the organization of the cosmic web. We have contemplated the past and the future, the known and the unknown, the questions we can answer and the mysteries that remain. If there is one thing I hope you take away from this exploration, it is a sense of connection. You are connected to the Milky Way, not just because you live here, but because you are made of its substance. The galaxy is not just your home. It is your body, extended across 100,000 light years. The stars are your distant relatives. The interstellar medium is your inherited wealth. The supermassive black hole at the center is part of your cosmic inheritance. This connection implies responsibility. We are the only beings we know of who can understand the Milky Way and appreciate its beauty. If we destroy ourselves through war or environmental catastrophe, that understanding might be lost. The galaxy would continue to turn, but there might be no one left to marvel at it. We owe it to the cosmos to preserve ourselves and to continue the great work of exploration and discovery. We also owe it to each other. Every human being is made of the same stardust, shaped by the same cosmic processes, part of the same improbable miracle. The differences that divide us are cosmically trivial. From the perspective of the Milky Way, there is no us and them. There is only us. One species on one planet in one solar system in one galaxy, trying to make sense of an incomprehensible universe. So look up tonight, if the sky is clear. Find the band of the Milky Way stretching from horizon to horizon. Let your eyes adjust to the darkness and see the countless stars that make up our galaxy. Know that you are seeing light that has traveled for thousands of years to reach you. Know that you are looking into the depths of space and time, at the very fabric of reality. And know that you belong here. You are not an accident or an aberration. You are a product of cosmic evolution, as natural and necessary as any star or planet. The universe made you through a process that took billions of years, and in making you it, made something capable of appreciating its own grandeur. You are the universe's gift to itself. That wraps up our journey through the true scale of the Milky Way. What an incredible voyage it has been, from the familiar distances of our solar system to the mind-bending vastness of the cosmic web. The galaxy that seemed so impossibly large at the beginning now feels like home, because it is home, the only home we have ever known. If you enjoyed this exploration of our cosmic neighborhood, please drop a comment below and share which part of the journey resonated most with you. Was it the staggering distances between stars, the mystery of dark matter, the inevitable collision with Andromeda, or perhaps the profound connection between the atoms in your body and the ancient stars that forged them? Whatever part spoke to you, know that this is just the beginning. The Milky Way has countless more secrets to reveal, and the universe beyond holds wonders we have not even imagined. The adventure of discovery continues, and you are part of it. You are the universe exploring itself, one question at a time, one wonder at a time, one moment of awe at a time. Until next time, keep looking up. There is something deeply moving about standing under a dark sky and seeing the Milky Way for the first time. Many people today have never experienced this sight. Light pollution from cities has erased the stars for billions of humans. They grow up knowing the sky as a black dome punctuated by a handful of bright points, never realizing the glory that awaits them beyond the reach of streetlights. If you have never seen the Milky Way, I encourage you to seek it out. Travel to a dark sky location, wait for a moonless night, and let your eyes adapt for at least 20 minutes. When your night vision is fully developed, look up. What you will see is a ribbon of soft light stretching across the sky, broader in some places and narrower in others, divided by dark lanes where dust clouds block the starlight behind them. This is not an abstract concept or a scientific diagram. This is your galaxy, visible with your own eyes, a direct sensory experience of cosmic scale. The light entering your pupils originated in stars that burned before humans existed, before Earth existed, in some cases before the sun existed. You are literally seeing into the past, witnessing ancient events frozen in beams of light. The experience can be overwhelming. Some people report feelings of vertigo, as if they might fall upward into the sky. Others feel a profound sense of peace, a connection to something larger than themselves. Still others feel fear, confronting the vastness of the unknown. All of these responses are valid. The Milky Way is large enough to hold all of our emotions. Throughout human history, the Milky Way has inspired myth and legend. The ancient Greeks called it Galaxias Kyklos, meaning Milky Circle, from which we get the word galaxy. They told a story of the goddess Hera spilling milk across the sky while nursing the infant Hercules. Other cultures saw it as a road of souls traveling to the afterlife, a river of light flowing through the heavens, or the backbone of the night holding up the sky. These stories reflect humanity's deep need to understand our place in the cosmos. Every culture has looked up at the stars and asked questions. Where did we come from? Where are we going? Are we alone? The questions are the same across time and geography. Only the answers have changed as our knowledge has grown. Modern astronomy has given us answers more strange and wonderful than any ancient storyteller could have imagined. The Milky Way is not milk or a road or a river. It is a gravitationally bound collection of hundreds of billions of stars orbiting a common center, embedded in a halo of invisible matter, surrounded by dozens of satellite galaxies falling toward a collision with another giant spiral. The truth is stranger than fiction, yet the modern understanding does not diminish the wonder. Knowing what the Milky Way actually is makes the sight of it more meaningful, not less. Those ancient photons gain significance when you understand their origins. Science and wonder are not opposites. They are partners, each enhancing the other. The more we learn about the cosmos, the more there is to marvel at. Every answered question reveals new questions waiting to be asked. Every solved mystery uncovers deeper mysteries beneath it. The universe is fractal in its complexity, offering infinite detail at every scale. Consider how much our understanding has grown in just a few centuries. 400 years ago, humans did not know that the sun was a star. They did not know that stars were other suns. They did not know that the faint band of light crossing the sky was composed of countless individual stars, too distant to see separately. They did not know about galaxies or the expansion of the universe, or dark matter or dark energy. In a few hundred years, we have gone from total ignorance to a sophisticated understanding of cosmic structure and evolution. We have measured the size and age of the universe. We have detected planets around other stars. We have found evidence for black holes and gravitational waves and the cosmic microwave background. The pace of discovery has been breathtaking. What will we know in another few hundred years? It is impossible to say. The history of science teaches us that predictions about future knowledge are almost always wrong. Things we thought impossible turn out to be routine. Things we thought we understood turn out to be mysteries. The only safe prediction is that our descendants will know things that would astonish us, just as our knowledge would have astonished our ancestors. Perhaps they will have direct evidence of life elsewhere in the galaxy. Perhaps they will understand dark matter and dark energy. Perhaps they will have sent probes to nearby stars or even established permanent settlements beyond the solar system. Perhaps they will have discovered things we cannot even imagine, concepts we lack the vocabulary to describe. Or perhaps humanity will fail, destroying itself before achieving these goals. The future is not guaranteed. We face challenges that could end our story, from nuclear weapons to climate change to engineered pandemics. The same intelligence that lets us explore the cosmos also lets us create weapons of unprecedented destruction. We are a species at a crossroads, capable of both transcendence and annihilation. The choice belongs to all of us. Every decision we make nudges humanity toward one future or another. We are all responsible for where humanity goes from here. If we survive and flourish, the Milky Way will witness something remarkable. A species that began as just another animal on a small planet will have become a cosmic presence, We will have spread beyond our birth world, carrying life and consciousness to places that have never known either. We will have become, in a sense, the galaxy's way of knowing itself. This is not an arrogant vision, but a humble one. We would not be conquering the galaxy or imposing our will upon it. We would be participating in it, joining the great cosmic dance that has been ongoing for billions of years. Every star that forms, every planet that coalesces, every moon that captures into orbit is part of this dance. We would simply be the first dancers who know they are dancing. The Milky Way does not need us. It functioned perfectly well for billions of years before we arrived and will continue functioning after we are gone. But perhaps there is value in being witnessed, in being understood, in being appreciated. Perhaps consciousness adds something to the cosmos that was not there before, a quality of awareness that transforms brute existence into experienced existence. We do not know if this is true. We do not know if the universe is better for having minds within it. These are philosophical questions that science cannot answer, but we can say that the universe with minds in it is different from a universe without minds. Something is happening here on Earth, and perhaps elsewhere, that is genuinely new in the cosmic story. You are part of that something new. Your awareness of the Milky Way is itself a cosmic event, a chunk of galactic matter contemplating its own nature. When you look up at the stars, the universe is looking at itself. When you wonder about distant galaxies, the galaxies are wondering about themselves. You are not just an observer of the cosmos. You are the cosmos observing itself. This brings us back to where we started, standing on our small planet and gazing up at an incomprehensibly vast galaxy. The Milky Way stretches above us, 100,000 light years of stars and gas and dust and dark matter. Within that immensity, we are specks, motes, barely existing at all on the scales that matter to galaxies. And yet we know we are specks. We have measured our insignificance and understood it. That understanding is not itself insignificant. In a universe that seems mostly mindless, mostly unaware, the emergence of comprehension is a kind of miracle. We are the Milky Way's way of understanding itself, and that is something. So as you go about your daily life, remember what you are part of. Remember that the ground beneath your feet is a planet orbiting a star in a spiral galaxy. Remember that the atoms in your body were forged in other stars long ago. Remember that you are connected to the cosmos in the most literal possible way, made of its substance and governed by its laws. And remember to look up sometimes,